I'm excited for this video, and I hope you are too. We're going to talk about combinations. Now, combinations are basically what happens if you have a permutation and the order doesn't matter. So if you remember, we had an example where we were talking about, how many ways can we make a movie schedule for if we have 30 movies and we wanted 3 movies that we're actually going to watch, and how many schedules are there of those 3 movies. So the order mattered here. But what if we're just curious about, how many combinations of movies can we watch in one night if we're only going to watch 3 movies? And in that situation, if you can think about these kind of as sets where the order doesn't matter for combinations. So let's say one possible movie night could be, maybe we start with Star Wars Episode 2. Maybe we move on to Napoleon Dynamite. And then we finish with Con Air with Nicolas Cage. But for purposes of combinations, right, this is the same exact set. If we don't care what order we watch these movies in, this is the same as if we watch Napoleon Dynamite and then Star Wars Episode 2 and then Con Air. Okay, so these are the same, and again, there's multiples of these. So if we don't care about the order and we're just curious about, well, how many groups of movies could we watch, then we're essentially double counting and triple counting here. We have a lot of duplicates in this 24,000. So how can we subtract out those duplicates? Well, there's duplicates for every single grouping of 3. So it'll actually turn out to be dividing. And furthermore, well, how many duplicates are there? Now this is where it's exciting. How many duplicates are there? Well, how many ways are there to order 3 things in a set? Well, we've already talked about that. We know how many ways are there to order 3 things. Well, there's 3 options for the first thing, there's 2 options for the second thing, and there's 1 option for the last thing. So there are actually 6 ways of writing the same movie night, assuming the order doesn't matter. We could watch Star Wars first, second, or third, right? We could watch Napoleon Dynamite then, whatever one of the other 2 is remaining, and then Con Air gets stuck in the last spot. So if the order doesn't matter, because again, let's get to the answer here. So if the order doesn't matter, we have the same answer as before, 24, 360. But for every single one of those possibilities, we're counting it 6 times. So we actually have to divide this by 6, and oh no, I didn't have my my Desmos ready again. Shame on me. 24 360 divided by 6 is now 4,060. So it's much smaller when the order doesn't matter. I've already forgotten the number. 4060. All right. So before, if the order mattered, there were 24,000 movie nights. Here, the order matters. There's only 4,000 movie nights. And this is what we're going to formalize with combinations here, where the order doesn't matter. Again, think of it as like the difference between sets and arrays. Sets, the order doesn't matter. Arrays, the order matters. So permutations are like arrays, if you want to think about it. And combinations are more like sets. So let's introduce what this is. Oh, not there yet. No skipping ahead here. No spoilers for anyone. So, actually, let's do one more example. One more example before you get the definition, I think. What about here? What about this race situation? There's 50 people. We care about how many ways there were of finishing top 10. Here, the order mattered. But if we're only curious about, like, hey, the top 10 go on to the next race, if we're only curious about how many groups of people are possible to go into the next race, then we don't care about, if someone got first or someone got 10th, it doesn't matter. They're moving on. So if we're just curious about who's going to the next race or something like that, we're going to have to get rid of the duplicates. So again, if we go do that race example again, we have to get rid of the duplicates. Well, previously there was this number, which is 50 factorial divided by 40 factorial. Right, there was 50 factorial over 40 factorial, because if the order mattered, there were 50 options and we were only choosing 10. all right? But again, just like before, we're double counting. So before we divided by 6 because there were 6 ways of organizing a group of the 3 that we were selecting. Well, now we're selecting 10, right? We're selecting 10. How many ways are there to order 10? That's what we're double counting by. That's what we're going to have to divide by. And how many ways are there to order 10 things? 10 factorial. So we have a very nice looking formula over here because 40 and 10 together is 50. So this is going to be our answer. And again, I'll probably use scientific notation here. 50 factorial divided by 40 factorial times 10 factorial is smaller than 10 to the 16th or 18th or whatever we had, but it's still a big number. Still in the millions. I'm not so good with millions and billions in scientific notation. But we have 1.027 times 10 to the 10th. Yep. So still a big number, but not as big. Still, if your boss says, I want you to find out, I want a list of all the possible combinations that are moving out of the next race, you say, no, boss, that's too many. There's a lot of combinations, even if the order doesn't matter. So I think this kind of hints at what our general formula for combinations looks like. Let's finally introduce it. So combinations are written as n choose k. All right, that's pronounced n choose k. You may have seen this before. You may not. You probably don't remember in either case, so here it is. And that's just n factorial divided by k factorial. Keep the notation consistent. N minus k factorial. This is what we've seen before, right? This was n to the k falling. The only difference is now we also have this k factorial in, right? This is the only new thing compared to partial permutations. The only new thing is we're getting rid of some double counting because order didn't matter. And that k factorial, right, is just saying, well, there were k ways of ordering the k that we took. So we divide them out so we don't double count. So we're going to finish this video with you doing some problems on your own. Pause the video, go through these problems, make sure you can do them. I'll talk through them afterwards, and that'll be the end of the video. So if you're confident you're good, this is it. Otherwise, here we go. The last one should be a little trickier here. You can pause the video here so you can actually see the problem. All right, let's see what we got here. How many 5-card poker hands are possible? Well, if you have 52 cards and you're choosing 5, and the order that you draw the cards or are dealt the cards doesn't matter, then yeah, there's n choose k. It's n choose k. Again, it's like a fraction, but there's no horizontal bar here. So that's just 52, choose 5. Also, I guarantee I will draw a horizontal bar so many times just on muscle memory. So that's 52 factorial divided by n minus k, which is 47 factorial, times k factorial. Again, these bottom numbers should always add up to that middle number or top number. And that's going to be probably a huge number. So if you want to type it in like this, you can. A lot of places also have, I actually don't know where it's going to be. A lot of places also have like ways of writing this. It's like here, n choose r. So we could do 52 choose 5, I think. Yeah. And that should be the same as 52 factorial divided by 47 factorial times 5 factorial. Great, they're the same. We don't need scientific notation. There's not that many poker hands, only 2.5 million. So we'll write equals 2,598,960. That many poker hands. All right, so memorize them all and become an expert. Actually, that's probably a very stupid thing to say. I'm not very good at poker. I don't know. Anyway, how about letter B? If there are 1,024 sectors on a disk, but you only have cache blocks for a quarter of them in memory, how many combinations, how many ways are there of, putting those sectors in memory? So the idea here is, again, very similar, right? We have 1,024 things, and we can only choose 256 of them. The order doesn't matter here. It's the same thing. All right, so you're going to do 1024, choose 256. You type that in, you should get the right answer. This last one's a little bit trickier. You have 4 or 5 people in a focus group. So we're going to look at all the focus groups of size 4 and all the focus groups of size 5, and we'll add them together. So this is going to be 10 choose 4. That's however many 4-person focus groups we can have. And 10 choose 5 for how many 5-person focus groups we have. And we're going to say that it doesn't matter who's, like what order they're in the group, but a group of 4 people is going to be different from a group of 5 people. So we'll add that up. And again, type in the formulas. You can get this on your own. Let me know if you have any questions, and welcome to Combinations.